So I would like to introduce Filippo, Sanfilippo from the University of Agder. I probably pronounced everything completely wrong, I think. People is talk about inverse kinematic modeling of a 3D real robotic manipulator using hybrid deep learning methods. So please give a broad thoughts.
Thank you very much for this introduction. I think that during this morning session, we had mostly articles presented that were more oriented to real production. This work here is going to be a little bit more research oriented. So it's my pleasure today to be here. And very briefly, I introduce myself. I am a professor at the University of Agder, which is located in the most southern region in Norway. And this is our research group. It's collaborative, it's biomechatronics and collaborative robotics research group. We are a small group, it's a small university in Norway. And in this picture, you can see I have organized research into 3 layers. So basically, the core layer that we work on is called as carriers layer. So here we have different kinds of robots, robots that are operating in aquatic environments, or bio-inspired robots like robots with legs or without legs, like the snake robot. And we also have some aerial vehicles. So these for us are just carriers. We can provide, we can equip these robots with different kinds of sensors. And that's why on the top layer we have the add-on layer, where we can, for example, have readers or manipulators or other sensors. But what we really care about is the interface with humans. So basically, we are not designing and developing robots just for the sake of designing them, but we want these machines to be operating with humans. Now we are navigating or surfing towards the concept of Industry 5, where humans become very central. So here we have our layer with different kind of interfaces, from human brain interfaces to devices that we have designed to provide tactile feedback, so that we can close the loop. So basically, we can control the robots, but we can also receive a tactile feedback in addition to visual, auditory, or other kinds of sensations. This is our team of PhD students. In the interest of time, I will dig into the content of today's talk. So first of all, I will introduce the topic. Then I will talk about the methodology that we introduced. And I will present some results and discuss them. And finally, I will be able to share some conclusions. So today we are going to basically investigate the concept of using machine learning algorithms to infer about inverse kinematics. So basically, I assume that there is that the audience in the room actually know about inverse kinematics, but just to summarize the idea here, when we operate a robotic arm, normally we have a target position or a target velocity, and we need to set the joint angles of our robotic arm. So we have a Cartesian target or a position or velocity in the Cartesian space, and we need to transform this into joint angles or joint velocities for the robot. So this is traditionally done with differential equations, but in this work here we are trying to use machine learning to actually learn about the inverse kinematics of the robot, because especially for complex manipulators with several degrees of freedom, it's a very complex problem to solve from a mathematical point of view. So here we want to see if we can learn this model by using machine learning algorithms. In particular, we are using a meta-heuristic approach combined with the deep neural networks. So here is the concept. So the idea is basically to use a simulator where we can build our robotic arm, and then imagine to think about a newborn baby, right? Normally, they will randomly move their arms. They cannot coordinate their arms and their arms. So basically, it's the same idea. We use a simulator to randomly generate poses for our robotic arm, and then we build our database. And based on this, we can then apply machine learning algorithms to infer or to learn the inverse kinematics of the model. So meta heuristics are just shortcuts, I would say. If you have a complex algorithm, you want to kind of split it into sub problems and solve them in a divide and inverse manner. So in particular, we are going to use a Gannett optimization algorithm as a heuristic, and we are combining it with the deep neural networks. A meta-heuristic algorithm is, as I said, a shortcut. We have different meta-heuristics that we can use. Some of them are single agent, some others are multi-agents. So for example, here we have the concept of exploring a multidimensional space to find the star, the blue star. So that's our optimum point. Obviously, meta-heuristics are prone to some challenges, like they can get stuck into suboptimal points, and there are strategies that we can use to avoid this challenge. So this is a standard neural network. I assume again that the audience is familiar with this concept. There is an input layer, an output layer, and some hidden layer in between. In our implementation, this is the configuration that we have used. So we have a single input and single output layer. We have hidden neurons, 10 hidden neurons, and 2 hidden layers. We have used the radial basis function as an activation function for the neurons, and we use the normal mean square error as a cost function. So basically, what we do is we have a target rotation or velocity. We measure the Euclidean distance, so the error between where the end effector is and where we want it to be. And then we use the optimizer and the Gannett optimization algorithm to iteration by iteration minimize this error. We run 50 iterations for each point. So here you can see in the plot how the optimization works and how the error decreases iteration after iteration. We have already mentioned the idea is to randomly move the robotic arm inside our simulator to generate our database of points. And here, particularly, we are using the robotic operating system, or ROS, and the connected simulation environment that is called Gazebo. And together with Gazebo, we use a tool that is called RViz, or ROS visualizator, which allow us to collect these setting points. So we randomly generate 1,000 points inside the simulator, and we split the data set into testing and training data with a ratio of 65 and 35%. So it's basically a quite straightforward approach. In these tables here, we see some of our results. We compare the meta-heuristic that we have used, the Gannett optimization algorithm, with 2 more heuristics. One is the gray wolf optimization algorithm, and the other one is the particle swarm optimization algorithm. These are both of them are agent-based heuristics, and the columns we have the three cost functions that we have used to do this comparison. We have the normal mean square error. We have the MAE and the mean relative error function. And as you can see in this table, is split into three joints because we are considering a robotic arm with three joints. So we have joint 1, joint 2, and joint 3. And for each of these, we see some advantage in using the Garnet optimization algorithm under our hypothesis. And here we see some more results with the tracking of the joints. So again, joint 1, joint 2, and joint 3. So on the upper plots, you see the green line is basically representing the actual position of the joint. And then we have the three optimization heuristics that we compared. The Garnet optimization algorithm, the gray wolf optimization, and the particle swarm optimization. And here, one of the metrics that we use for comparing these algorithms is the relative error. So as you can see, the blue line is really close to zero, except for some spikes. And these spikes can be possibly motivated by the fact that we reach singularities. So singularities are situations where you have multiple solutions. So for example, if this is my robotic arm and I want to reach this point, I can reach it in this way, but I can also reach it this way or in other ways. So there are multiple solutions, and that's where we normally record bigger errors. There are strategies that we can use to minimize these problems. So for example, we can add the concept of task-oriented manipulation. So for example, if I am going to grab a coffee cup, right, with a robotic arm, there is no reason for me to grab it from this way, right? Because I cannot use it. So it's normally better to eliminate some of the possible solutions. So I reduce the singularity problem. So just to conclude, in this work, we have implemented the metaheuristic algorithm based on the Garnet optimization approach, and we have combined it with a deep neural network to solve the inverse kinematic problem of an industrial robotic lab. We have compared it to two more meta heuristics, the gray wolf optimization algorithm and the particle swarm optimization algorithm. And we have implemented this into a simulator environment, which used the already quite established robotic operating system and the gazebo simulator. We have done some preliminary results looking at the tracking of the joints, and the performance seems to be promising. We need to obviously test this with a real robot, and we also need to see how the algorithm can scale to a bigger number of degrees of freedom. Here we have used 3 degrees of freedom. How does it scale to a more complex manipulator, for example, an industrial manipulator with 7 degrees of freedom? As a future work, we are going to explore these possibilities, scalability, and testing with a real robot. And with this, I conclude my presentation. I'll be very happy to answer your questions.
So, thank you for the talk. Any questions?
Thanks for the very nice talk. You mentioned this just in point two of the summary, that we created the data set based on ROS. So did you set robot joint angles and let ROS calculate the forward, the direct kinematics, and then have a set of joint angles and XYZ position to use for training?
Precisely. So basically, we random generate 1,000 points, and then we, for each of these, we let the end effector reach that point, and then we measure and store the corresponding angles. That's one sample in our data set. Yeah.
So, do you think it's the most effective method to do? I would do it via an Excel table.
I would not call it maybe the most effective method because it takes you have to repeat 1,000 iterations. There might be other possibilities. So, for example, you could use differential equations or a numerical approach to do this, so you don't have to simulate it. It could be also possible, but in the simulator, I would say we also include some more realistic aspects, because, for example, imagine that we could use this with a less traditional robot, maybe a soft actuated robot. So that would be very much more complex to simulate, to do it numerically or with equations, right? But
From you gave was like 4 or 5 for this robot. You have 3 equations to transform from joint to X, Y, Z, and back. So yeah, in my opinion, it's not necessary to use a ROS.
yeah, so as I said, in ROS,
Maybe for more complex robots.
yeah, I agree. I mean, I partially agree. And the idea is that when you use ROS and a simulator, you can, for example, also simulate collisions, and I mean, you can approximate, you can have a more realistic simulation compared to the real world, right? So in the real world is not ideal, it's not idealized in mathematics. Yeah. Okay.
For inside, probably similar question, very interesting approach, but I would be interested if you have some special application like this or anything else where you think that this approach has advantages compared to just the analytic versus kinematic, because for 3 degree of freedom, I guess that you would be able to do an analytic solution.
Sure. Yes, as I said, this is just a starting point, and definitely the case with soft robotics is a very interesting case, and we are working towards this direction now. We are designing some robots that are kind of hybrid, so we use rigid motors, but the shaft of the motor is connected to a torsional spring, so that you have some range of softness or flexibility. So I think that case would be a nice case to explore.
Any other questions? If not, then give a round of applause.